Hello, chemistry. I did a short screen capture of the PHET reactions and rates app just in case we had any difficulties with it crashing during class so that I had a plan B, or in case you want to go back and use this to review. I'm just going to run the same things that we did in class though, so there's nothing new here. We started with 20 particles each of our reactants, A and BC. And remember that this is an equilibrium reaction, so it's not all going to just progress in one direction. We'll see some sort of balance point achieved, but this is, as you hopefully know, a single replacement reaction. So we have a reaction pathway graph here on the bottom where we start with the reactants on the left, and then the reaction progresses towards the products on the right. In order for the reaction to take place, the reactants have to achieve a certain amount of energy to get it going. And so the difference between the starting point and the top of this peak is called the activation energy. So there's an activation energy going from reactants to products, and then there's also an activation energy for the reverse reaction. And in this case, the forward activation energy is actually greater than the reverse. But our progression does go left to right, and because we end at a higher energy than where we started, that means that these substances have taken in energy over the course of the reaction. That means it is an endothermic reaction. Endothermic reactions are more difficult to achieve just because you're kind of going backwards. Natural systems, we'd expect the energy to go down. And in fact, the energy does go down from the top of the activation peak to the end, but you do have to do quite a bit of work in the beginning to get the reaction started and actually complete. So let's go ahead and let the app run, and we see at a fairly low temperature and a fairly high activation energy, things don't happen quickly. The particles are colliding, but the collisions aren't overly effective. We start to see a little bit of product buildup here, but nothing's happening too quickly in this reaction. So it's one that definitely favors the left-hand side, and we're not progressing at a very high rate. So let's take the same conditions and let's bump the temperature up a bit, and let's take it maybe up to here and go ahead and start the experiment. So what we've done really is give the particles a head start. We worked them up the hill, and we can see now that we're producing more products at a lot higher rate. So as we would expect, raising the temperature makes the particles, the collisions more effective, and that change in the amount of reactants versus products happened a whole lot more quickly this way than the other. We're still favoring the left side because it's much more difficult for the particles to go from left to right than it is from right to left. So we see a lot of unreacted A and BC floating around more so than the AB plus C products. Let's go ahead and customize this a little bit. So now you see that we've changed the graph and gone from an endothermic reaction to an exothermic reaction. So I'm going to change the values a little bit on here to make it more like it was in the initial graph. I'm going to actually scoot this down. Let me scoot it down. There we go. Bring this down a little bit and this down a little bit, so I can work with this later on. So there we go. So this is a little bit more similar to what the last example was, just in reverse. So let's take a look at this and see what happens. We notice that this time it's a lower activation energy to go from left to right than it is from right to left. So we're going to favor the right side of the equation. And because the activation energy is lower, even at this colder temperature, it's a little easier for the collisions to be more effective. And we see that the reactants and products build up pretty quickly. Same thing though, if I take the temperature and I bump that up. Let me do that. If I take the starting temperature and I bump that up, say to here, and we begin the experiment, wow, the reaction takes place pretty quickly, and we get to that right side favoring balance point pretty quickly. Matter of fact, it seems to bounce around even more just because so many particle collisions are effective at this high temperature that it's kind of can bounce back and forth between each side of this little hump pretty easily at that starting temperature. Might have gone a little overboard. So what happens if so let's just give ourselves a baseline. Let's go from right about here and start it again. And we say, all right, they're going along, and what are we, 5, 6, 7 seconds, and we've progressed to the equilibrium of the reaction. And that, let me take this activation energy and bump it way up, and let's see what that does to the rate of our reaction. 1, 2. There you can see already, without me having to count, that the rate is much slower because it's much more difficult for the collisions to be effective because the activation energy is higher. This is the effect that adding an inhibitor would have on a system. An inhibitor effectively raises the activation energy, makes it less likely for each collision to be effective, and therefore will slow down the overall rate of the reaction. Does not change the reaction. I did not change the starting or ending point. All we did was raise the hill, and that is the effect of a chemical inhibitor. But it's the same reaction, same A's and B's and C's, and therefore the same exothermic reaction start to finish. A catalyst would do something similar. A catalyst doesn't necessarily change the activation energy directly. It just gives the reactants a different path that is a lower activation energy. So really it's the same thing as if I take and I lower this hump down. So we have a lower activation energy along a different path. I've added a catalyst to it, and so now if I begin the experiment, it goes in just a matter of a couple of seconds in the simulation. We've headed back toward the equilibrium point. A little bit of a right side favor because it's easier to go left to right than it is right to left. So this is the basics of a reaction pathway graph. Inhibitors and catalysts will affect the apparent activation energy. The activation energy is what's needed to actually get the reactants to go from one side to the other. This is a very simplified case. Truth be told, in a reaction, there's going to be several different places where the bonds have to break and where they form. So the graph is not necessarily going to be smooth. It's going to be a bunch of little peaks, and each one of those little peaks is a step in the reaction that has to occur in sequence for the overall reaction to follow its pathway from reactants to products. It's a fun app. If you can get it, I'll post a link to it if you can get it and play around with it. But it really ties together a lot of parts of collision theory and the Arrhenius equation and temperature's effects on reactions. I also could do pressure's effect on reactions, and this is the fun part. If we want to increase pressure inside of here, I can just say, well, hey, let's add some more A and pump it up. There we go. Pressure, pressure, more collisions, more reactions, all sorts of fun stuff going on. Take care, guys, and stay safe.